So our next speaker is Nicola Assolini, and he will be talking to us about static analysis of quantum programs.
Okay, hi to everybody, and I'm Nicola Assolini. In this talk, we'll talk about how we can use some static analysis, in particular some data flow analysis, to solve some problems that are specific to quantum programming and program with quantum variables, basically. So let's start from the beginning. When we are talking about quantum programming, in general, what is really quantum is basically the variables. And so this is a big difference with classical computing, since in classical computing the variable are basically some logical abstraction or the memory, and so they are referred to some logical representation of the memory that is a logical representation of a physical device that use electronic signals, and in which there are, from the program language point, we basically don't care about all the physical stuff that are inside a classical memory, basically. In quantum computing, this is a bit different. In fact, the quantum variable are an abstraction of usually some wires in a quantum circuit, or we can use some different models. But at the end, these quantum variables are referring to some quantum particles. So when we work with quantum variables, we cannot ignore the physical meaning of the variables, since there are some features specific to the quantum computation that we need to take in account also in the high-level view of the program. In particular, we need to take care to two features of quantum computing, that is a theorem and a principle, that can make the use of quantum programming and the design of quantum language a bit more difficult. In particular, these two things are the no-cloning theorem and the implicit measurement principle that create some problem together with the entanglement. Let's start seeing in detail these two theorems. The first theorem is the no-cloning theorem that, as the name states that given a quantum particles, we cannot create some procedure that take the quantum particle and produce two particles that are identical to the first one. So basically, this means that we cannot freely copy a quantum value. So in quantum programming, we can see an example. When we are working with classical data, we can have a program like this one, in which this variable a corresponds to some classical data, and we can copy the value, compute h of a, and assign to b, doing the same of c, and we can go on. In quantum variable, we cannot do this. In fact, if you have the variable a that is a quantum variable and represent a quantum data, we cannot copy them to compute h of a without changing the value of a. So to compute the program, we need to apply this function that could be some quantum function directly on the particle that is represented by a, because we cannot copy them. So in this case, after we compute b equal to ha, we have basically changed also the variable of a. That is as similar in classical computation when we are working with pointer instead of using a call by value, for example. So basically in quantum, since we cannot copy the value, the actual value of a variable, every time we work on a variable, we also change that variable, even if we have a command like this one. So in this case, after this command, if you want to compute c equal to ta, we cannot actually compute this value. We can compute something different if we decide that a is still valid, but a at this point is not more the original value, but is something else. So in general, if we want to avoid having some side effect similar to what we have with pointer, due to the no-cloning theorem, we cannot use if we decide that we don't want to change the value of the variable not as implicitly, we cannot use a variable more than once. The other principle is the implicit measurement principle that say that in a quantum circuit, every wire at the end must be considered measurement. In practice, we can see on an example what this means. If we consider this circuit that computed this Boolean expression, in this circuit we have 2 wires from the input, 1 wire for the output, and a temporary variable that we need to compute the circuit. We have the first operation that computes the XOR between X and Y, and the second operation that computes the AND between A, that contains XOR, and Y. So if you look to this circuit, we need a temporary variable. We can compute the Boolean expression. We obtain this state that, since the initial state is a quantum state with a superposition, also the final state is. You see that here R, that is the third value, contains the result of a Boolean expression. Of course, we have a superposition of result. And at this point, we have computed what we need. And the variable, the temporary wires A, is no more needed. So if you want to reason as in classical computing, we can drop it. But due to the measurement, to the implicit measurement principle, dropping a wires imply making a measurement. So if we make a measurement of the state of A that is in superposition, we can have different result according with some probability. In particular, we can have 0 or 1, but here A is entangled with the other variable. So if this implicit measurement cause A to collapse to 0, also the rest of the state will collapse to 0. If here A collapses to 1, also the rest of the state will collapse to 0, 1, 1. So basically, this operation that drop a variable broke the state, because here we don't have anymore the superposition, a result in superposition, but we have a probabilistic distribution of 2 classical states. And this is not what we want, because if this is an intermediate operation of some computation, here we don't have what we expect to have. So how we can solve this? We need to add an extra procedure to our program that is called a computation. This procedure basically reset the value of A. So now A is 0, is no more entangled with the rest of the variables, so we can drop it with causing a measurement. But this measurement does not alter the state of the rest of the program, since A now is not entangled. So in a high-level view, the implicit measurement principle implies that if we have a program, we need to take care which are the variables that are temporary, in order to pay attention when we drop this, when we decide to deallocate this variable. So in general, we can we need to take care when there is a discarding of some variable. So now we have 2 constraints. The first constraint that say that we must use variable at most once, and the second constraint say that we cannot implicitly discard a variable, since we cannot just dropping it. If we put together this complaint, we obtain that we must use all variables exactly once, because this constraint imply these 2 conditions. And in fact, the standard solution in the literature is use linear types for quantum program. In fact, in the first case, if you have a program that uses a variable twice, a linear type checker will discard this program since the variable is used twice. So we are okay. Similarly, you have this program that corresponds to the circuit that I showed before, in which we use a temporary variable A, and then the last time we define it, but we never use it, and we don't return it because A is not more needed. A linear type checker will discard this program since it says that I is not consumed, means that A is not used. And in particular, the second case is more interesting, because here we cannot do anything basically. We have write a program that we cannot directly translate in a quantum computing on a quantum computer. So if you want to run this program on a quantum computer, we basically need to change the program. So to decide a way to compute this program, to translate this program in something that is quantum computable. But in the second case, we can do something. In fact, usually linear type program with linear types always have some function that can be discard or forget, it depends of the program, that allow us to delete a variable during the computation. So in this case, this program is correct because we use a temporary variable a and we discard it when it is no more used. But when we work with linear types, the type checker only do a check. Of course, it's a checker. And so we have to manually insert all the discard where are needed. And okay, if you have a simple program like this, it's easy. We can simply discard it after the last use. But if you have a program with a complex control flow, it may be difficult to understand in which path some variable are used, which path are not, and adding all the discard. And also the task of adding the proper discard is something that can be done using only information that are always statically available without executing the program. For this reason, in order to make the use of the quantum language easier and avoiding some work and avoiding that the work of inserting all the discard must be done by the programmer, we introduce a static analysis that collect all the information that are needed in a program. And basically, instead of, when we have a program like this, instead of returning an error, we analyze it, detect which are the temporary variable, and add a discard. And thanks to this, we can basically relax the constraint of using variable exactly once and only force the programmer to write a program that uses variable at most once. Since this is something that it cannot be done automatically, since it means if you have a program that uses a variable more than once and I want to make it, I want to transform it in a program that uses variable at most once, I basically change the semantics. But this transformation that simply add a discard is something that can be do automatically. So how we did this? We do this defining using a data flow analysis, because we need to understand which are the variables that are not fully used. In particular, since we are interested in understanding the use of a variable, we start from liveness analysis that I can briefly recall. In general, we say that a variable x is live in a program point if it has been defined before, and it will be used in the future path. So here x is live because we define it before you and we use it after you. For our purpose, the liveness is not enough, but we need to define a most refined type of liveness analysis. In particular, we need to define two types of liveness that we represent with a pair of set. The first set of the pair represents the variables that are safe live, and in particular, we say that a variable is safe live in another U if it will be used in all paths after the node U. Instead, we say that a variable is unsafe live if it's live in a node, but there is at least one path that does not use it. So in this case, X is unsafe because it uses only one path but not in the other. So let's see how we use this analysis for our purpose. We start from this program. This is a simple program that takes 2 qubits, a Boolean bit as a condition, and basically according to the value of B, apply this function x to R or Z, store the result in C, and then compute another operation and return U. In this program, we have 3 implicit discarding. We implicitly discard R, since R is used only in one path. So when the B is false, the computation go to the else. The else does not use R. So basically, R enter in this function but does not exit from this function. So we implicitly discard R. For the same reason, we implicitly discard Z because we don't use it in the if path. And then we discard C because we define it in the last time, but we never use it. So a linear type checker will return these 3 errors on this program. Let's see how we analyze this program. First, the first step is transform this program in a control flow graph. So we basically put every instruction on an edge. We add a special label to indicates the condition. So this is the true branch, this is the false branch, and also this label that say which are the argument of a function. So our analysis is based on liveness analysis, so it's backward. We start from the end node. We initialize to void both pair because at the end no variable are live. Then, similar to aliveness, every time that we use a variable, we add to the set S. When we define a variable, we remove it from the set. Here we remove C, for example, and we add R and Z. When there is a join, if a variable is safe in all paths that we join, we put it in S. Here U is safe, so it's safe also in the join. If a variable is safe only in one path, this means that in the join it's no more safe, because it's used only in one path. So we put it in unsafe. And here we go on, like aliveness, every time there is a definition, we remove the variable because it is no more live. At this point, we know, basically we have all the information about the variable usage of the program, and we need to add the discard function. In particular, there are two types of variables that must be discarded. The variables that are never used, so the variables that are not live, and the variables that are partially used, so the variables that are in the second set. Because these variables are used in some part of the program, but there is some path that does not use it. So in some path, some of the possible path of the program, there will be a implicit discard. So let's see in this example. First we search for not live variable. How we know that a variable is not live? We check after all the definition if the variable is in one of the two sets. So here all the definition, here U is live, is used, in fact is live. C, it will be used, in fact is live. The second C is never used, in fact is not live in 6. So this C is never live, and we can add the discard just after the definition, because it's never used. In the second case, we need to check for the variables that are in U. In this case, R and Z. Let's see R first. Here we see that R is unsafe in node 1 and node 2. And it's safe in node 3 and not live in node 4. This means that if R is in U, it means that there is a path that does not use it. So how we find this path? We look when the variables stop being live. So here is live in the successor is okay. Here is live in 3 is okay. Is not live in 4. So this means that the fact that R is unsafe comes from this path. So we can add the discard at the end of this path. The safe is must be safe. So we intersect the first set of the pair. The unsafe is maybe unsafe. So we join the set U, meaning in this case is void, and we add the symmetric difference of the set S. So here we make the intersection between safe and the union between unsafe that is void, plus the symmetric difference, so R and Z, and we add in U. So it must be safe and maybe unsafe. And if we join these two sets, we obtain the liveness in general. So in this case, since R is not live in 4, it means that this is the path that don't use it, so we can add the discard. We do the same with Z, that is unsafe, safe, but not live. So this is the path that don't use it. So basically what we have done, we have started from this program that a type checker will discard, saying returning at least 3 error, and without any intervention of the programmer, using only information that are statically available with data flow analysis, we have added the 3 discard function where they are needed. So this was the main result of this paper, that take a program, perform the uncomputation analysis, insert the discard, and return the program with the extra instruction that makes this program correct from a quantum point of view. In the paper, since we start from the language that are built for linear types, we start from the hypothesis that all the variables are used at most once. So, and instead of saying that, okay, this constraint can be checked with a relaxed type system, so not a fully linear type system, but with just a type system that check that the variables are at most alive, we have also introduced another static analysis that basically do this check. So the complete pipeline of our work is takes the program, check if there are some variables that are used more than one. If there are, we can only return an error because we cannot change the program only using the information that we have. If this constraint is fulfilled, we can proceed performing the analysis that I have just shown, and insert the discard function, so adding what we miss to have a correct quantum program without returning any error. What we use to check the use of variable, we use a pretty simple static analysis. Basically, every time, this is the program that I use that I showed before, that is not correct because we use the variable a twice. Basically, in this analysis, every time we define a variable, we add to a set. Every time we use the variable, we remove it from the set. So if we use a variable twice, when there is a use, that use a variable that is not in the set in the previous node. So we can easily check if this is. And in this case, since we want to be correct, if there is a join, we do the intersection between set. Because when we use a variable, we want to be sure that this variable is available in all possible paths. So concluding, we have introducing this pipeline based on static analysis to check if the program is correct from a quantum point of view. In particular, to check if the program does not use a variable more than once, and to automatically transform this program in a program that also contain all the functions that at compile time, that on a high-level point of view add the discard. That means at the end of the compilation process that the final circuit has all the computation, so we don't introduce unintended measurement and so potentially error. In particular, we believe that using static analysis instead of a type system, like it's done in most of work, could be an advantage. In fact, our analysis are basically are data flow analysis. So like a type system, we must consider always all possible paths. And so we can have false positive like a type system. If, for example, we have some condition that is always true, always false, we can have a false positive. But since we are using static analysis, we believe that our approach could be easily integrated with some other analysis that could be like some constant propagation or interval, this kind of analysis, then can help to detect if there are some conditions that are always true, always false, or for example can help in abstracting the loop, because with a constant propagation we can know if a loop is for sure done. I mean, at least for some, we can better represent the loop, and in this case we can improve the checking first, so we can avoid to return some error that are not actual error, and also we can avoid to introduce the discard in part of the program that are not really needed. And also we plan to integrate this approach with some other analysis more from the quantum side. In fact, we have seen before, all the discard problem happen only when the variable that we are implicitly discarding is entangled with the other. So we believe that adding another static analysis that detect the group of entangled variable could help, because basically if a variable is not entangled with the other, we can simply drop it without any effect. And that's all.
Thank you for the talk. We have time for plenty. We have plenty of time for questions.
In the classic data flow analysis,
Yes.
liveness or deadness, it's syntactic.
Yeah.
And the formula is not something or something. And they over-approximate both,
Yes.
and which, when you negate, becomes an under-approximation, and so it's incorrect. For example, if x is 0 and you reassign x, it does not count, whereas syntactically it counts for a modification. So to have a true liveness in the meaning of the semantics, you need to take values of variable into account. In classic, do you have the same problem?
Okay, I don't think so, because basically we start from we basically, before performing our analysis, we have this other analysis that mean the fact that we cannot use a variable more than once avoid this kind of problem. And basically the only because we know that a variable is, or a variable is never used, or it used once. So what we mean, so thanks to this fact, we can avoid this kind of problem. Yeah.
More questions?
It's continuing a little bit in the same direction as Patrick, because you're using good old classical techniques to reason about something which is eventually a quantum computation.
Yes.
So if you wanted to argue the full correctness of this, you would have to link it to the semantics of the quantum computation, I would say. So, or at least you have to argue that you can get back to the classical world and then do your analysis. So how does that work?
Can you repeat the question?
How do you link it back to? Do you have to link it to the semantics of a quantum computation?
Okay. Basically, I mean, this is a data flow. Okay, I mean, basically, this is a data flow analysis, and in general, I mean, we use this NIP, this small fragment of program comes from a program that is called Guppy, in which the control is always classic. And since our analysis is a data flow analysis, basically from the analysis point of view, we don't care, or we don't care about the quantum part, because we don't have to. I mean, what we have to detect is understand if there are some variable that are not used, because we know that this kind of things cause problem in the quantum.
Right. So it's perhaps this knowledge. How do you formalize that knowledge, or has anybody else formalized that?
Formalize what?
This thing that you can talk about a quantum computation with classical means.
Okay. Okay. I don't. Yeah, exactly. Okay, and also the fact that the implicit discard things happens is something that is related to the quantum part of the classical part of the quantum program. So from this point of view, we actually don't care about the quantum semantics, because it's basically the program is a classical program or probabilistic program. We can also put some measurement, so it's become probabilistic, but the flow is classical with some quantum operation inside. But what we want to find is that there are not implicit discarding, so there are not variables that are unused, and the fact that some variables are used or not used is something that is more classical than quantum, because it's dependent to the control flow and to the syntax. That could be a more quantum analysis in which we need to take account of the quantum semantic of the problem, because if we want to analyze the entanglement, we need to abstractly represent it, and we also need to do an abstract semantic of the entanglement. So in that case, we cannot simply look into the control flow, but we need also to have an abstract semantic. Okay. Yeah. Okay, yeah. Yeah.
All right, let's thank our speaker again.